Alright, let's do this. Let's start off by naming each compound and then drawing the Lewis structure. So the name of this, we have one oxygen and we have two fluorines. So therefore the name is going to be oxygen difluoride. So we only have one oxygen, so we don't have to say mono, not for the first one. And then because there's two fluorines, we're going to call it difluoride. Now let's draw the Lewis structure for it. So the trick to drawing Lewis structures is this. The first thing I do is count up all the valence electrons that are going to be present in this molecule. You cannot skip this step. So let's just count them up here. What we have here is, let's see, oxygen brings in 6, plus fluorine brings in 7, plus 7, that's 14 plus 6, that's 20. So we have 20 valence electrons that we have to account for. We cannot use some of them, we have to use all of them, and we cannot use more than that. So now the next step is take the atom that needs the most electrons, in other words that has the fewest valence electrons, that usually is going to be the one that's written on the left, and put it in the middle of the structure. So I'll put oxygen in the middle, and then I will symmetrically distribute the other atoms around this central atom. So in this case I'll put one fluorine here and one fluorine here. If it was OF3, I'd put one here, and one here. And if it was OF4, I'd put one here, one here, one here, and one here. But it's just OF2. So here you go. I'm going to put a fluorine here, and I'm going to put a fluorine here. Now the next step is to connect the central atom to the peripheral atoms with single bonds. And remember, each single bond is 2 electrons, a shared pair. So we have 2 electrons here, 2 electrons here, and now that we've connected them with single bonds, we distribute the remaining electrons in pairs until we run out of electrons. So in this case we're going to say we have used up 2, 4, now we have to get all the way to 20, so let's keep counting. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now you'll notice everybody's happy here. I've got, let's count how many electrons we have. 2, 4, 6, there's 8 around fluorine, so it has an octet. 2, 4, 6, 8, there's 8 around oxygen, so it has an octet. 2, 4, 6, 8, so it has an octet. If any of the atoms didn't, we'd have to do something more, which we'll see with our next one. So let's go on to number 2 is this one here. I have 1 oxygen and 2 carbon, so it's going to be just like this one here. It's going to be called carbon dioxide. So I only have 1 carbon, so I just say carbon, and I have 2 oxygens, so I say di and then oxide. Now again, what we have to do is we have to count up all the valence electrons. So what we've got here is 4 electrons, valence electrons for carbon, plus oxygen has 6, and I have 2 oxygens, so that's a grand total of 16 valence electrons. I don't have any more than that. I have to use all 16 of these. So I'm going to take the atom that has the fewest valence electrons, carbon, and put it in the middle. I'm going to distribute the oxygens symmetrically around the central carbon atom. I'm going to connect these peripheral atoms to the central atom by single bonds. Now remember, each of those single bonds represented a pair of electrons. So I've just used up 2, 4 electrons. I'm going to distribute my remaining electrons in pairs, making atoms happy as I go until I run out of my electrons, which is 16. So again, what I've got is 2, 4, 6, 8, 10, 12, 14, 16. Whoops, I just ran out of electrons. And you'll notice carbon is not happy. Carbon only has 2, 4 electrons. I have 2 sides that don't have any electrons on them, so that tells me I am, now here's a trick, ask yourself how many pairs short am I? This carbon is 2 pairs short of an octet. So for each pair short, here's what we're going to do. We are going to add a bond. Since we're 2 pairs short, we're going to add 2 bonds, and I have to erase 2 pairs of electrons in order to do that because I don't have any extra electrons. So let me see if I can figure out how to do this. Okay, I'm going to erase a pair here and a pair here, and look what I've got now. 2, I should also point out that when we add these two bonds, notice we put them symmetrically around the carbon instead of putting 3 on one side and just leaving 1 on the other side. It turns out molecules prefer to have single bonds. If they can't form with single bonds, then they'll go to double bonds, and they will only go to triple bonds if there's no way to do it with single or double bonds. So let's go on to the next one. Here we have just CO, so let's give it a name. In this case, it's going to be carbon, since there's one of them, and monoxide. When we only have one of the second one, we use the prefix mon. We don't use the prefix mon for the first one, but we do if there's just one of the second. So we have carbon monoxide. Let's count up our valence electrons. We always start off by doing that. I have 4 for carbon, plus I have 6 for oxygen. That's a grand total of 10 valence electrons. Now I can't put in the middle since there's just 2, so here's carbon, here's oxygen. I'm going to connect them with a single bond. That's 2 electrons. 4, 6, 8, 10, and I just ran out of electrons. I only have 10 to work with, and there they are. So if I look, oxygen has 2 sides that don't have pairs. Oxygen is missing 2 pairs. It has 2, 4, it wants to have 6, 8. So since I'm 2 pairs short, I add 1 bond for each pair short. Since I'm 2 pairs short, I'm going to add 2 bonds. Now to get those electrons, I'll have to get rid of 2 pairs because they had to come from somewhere. So I'll get rid of this pair here, and I'll get rid of this pair here, and there's what carbon monoxide looks like. It could only be made with a triple bond. Okay, let's go on to the next one, number 4, P2I4. So we're going to name this compound diphosphorus tetraiodide. And the reason we're going to name it that is because we have 2 of the phosphorus, so I have to use a prefix di to tell me that there's 2 of them, and then I have 4 of the iodine, so I use the prefix tetra to tell me that there's 4 of the iodines. So now let's draw us a Lewis structure. Remember, the first thing I have to do is count up the valence electrons. So I see that phosphorus has 5, and I have 2 phosphorus, so I'll say 5 plus 5, plus I have iodine that has 7, so I'll say 7 plus 7 plus 7 plus 7. So that means I've got 28 electrons from the iodine plus 10. That's 38 valence electrons to work with. Good golly, that's a lot of them. Well, sorry, I just took a sip of coffee. Here's what I do differently. Now in this case, I have 2 phosphorus. Now notice, phosphorus has fewer valence electrons than the iodine, so it's going to go in the middle. However, there's 2 of them. Since there's 2 of them, I put them both in the middle, like this. I'll put a phosphorus here, and I'll put a phosphorus here, and I'll connect them together with a single bond. Now I'm going to treat this as the center of the molecule, and I'm going to distribute these iodines symmetrically around this core. In other words, I'm not going to put 3 iodines here and 1 over here. I'm going to put 2 here and 2 here. You've got to try to make your molecules symmetrical when possible. So I'm going to put an iodine here, and an iodine here, and an iodine here, and an iodine here. Now what I'm going to do is I'm going to connect them to the center with single bonds, like there, 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 and there. Alright, let's count how many of these 38 valence electrons I've used so far. I've used up 2, 4, 6, 8, 10. So I still have 28 to distribute. So that's 10, 12, 14, 16, 18, 20, 22, 24, 26, can you see this one over? 28, 30, 32, 34, 36, 38, and my golly, you'll notice everybody's happy. You look, everybody's got a pair of electrons on all 4 sides. So I didn't have to resort to any double bonds. So there's my diphosphorus tetraiodide molecule. Not as hard as it looked like it would be. Oh, I've got a stray mark I need to erase. Hang on a second here. Alright, let's try our next one here. Ooh, carbon compounds can be tricky. Alright, so the first thing I'm going to do is I'm going to try to name this. Now, in truth, when we go to name carbon compounds, they have their own naming rules. So organic compounds, as they're called, have their own naming rules. However, we're just going to go ahead and use the convention that we've been learning. So let's see what I'm going to call this. So using our naming convention, we would call it dicarbon, since there's two carbons, dihydride, since there's two hydrogens. In fact, in carbon chemistry, we call this the ethyne molecule, or we also call it acetylene. But we're not going to worry about that right now. We're going to call it dicarbon dihydride. So let's go ahead and draw this sucker. The first thing I've got to do, count up the valence electrons. I've got 4 from that first carbon, plus 4 from the other carbon, plus 1 from the hydrogen, plus 1 from the hydrogen. That gives me a grand total of 10 valence electrons to work with. I'm going to put the carbon in the middle, and there's 2 of them. I'm going to connect them with single bonds. I'm going to distribute the hydrogen symmetrically around it, and then connect it to the core with single bonds. Let's count up how many of my valence electrons I've used. 2, 4, 6. I'm going to distribute the remaining in pairs until I get to 10. So 2, 4, 6, 8, 10. Hey, how many pairs short am I? If you look, I'm 2 pairs short. Wait, you're saying, what about hydrogen? Now, hydrogen doesn't follow the octet rule. Hydrogen wants to look like helium, and helium only has 2 valence electrons, so this is what happy hydrogen looks like. Happy hydrogen is a hydrogen with a bond, because that's 2 electrons, and that's all it wants. So I look here, carbon is 2 pairs short, so for each pair I'm short, remember, I'm going to add a bond and erase a pair, and since I'm 2 pairs short, I'm going to add 2 bonds, and I'm going to erase 2 pairs, and that's what my molecule is going to look like. Okay, ready for number 6? So let's just name this particular atom here. This should be fun. And we're going to call it diarsenic because I have 2 arsenics, tetraoxide because I have 4 oxygens. Really, all I had to do is use prefixes to tell me how many of these. Now, we're going to count up valence electrons. Oh boy, here we go. Alright, we got 5 for the arsenic, plus another 5 for the other arsenic, plus 6 for the oxygen, plus 6 for another oxygen, plus 6 for another oxygen, plus 6 for another oxygen. So that gives me 24, that gives me 34 valence electrons to work with. I'm going to put the arsenics in the middle. I'm going to connect them to each other with a single bond. Now I'm going to symmetrically distribute the oxygens around this core. So I'm going to put an oxygen here, and an oxygen here, an oxygen here, and an oxygen here. I'll now connect the oxygens to the center with single bonds. Now I want to count and see how many of my 34 valence electrons have I used so far. I have used 2, 4, 6, 8, 10 of them. So I'm going to distribute the remaining in pairs and stop when I get to 34. So I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. I just ran out of electrons. Now you may think this looks like a happy molecule, but it's not, because if you look carefully, what you'll notice is I have arsenics are not happy. I have 2, 4, 6 around this one, 2, 4, 6 around this one, so they're not happy. Now I need to add 2 bonds and erase 2 pairs. And remember, I don't want to go to triple bonds unless I'm forced to. And at this point, I am not forced to go to triple bonds. So instead what I'll do is this. I will add 2 more bonds, one here and one here, and I will erase 2 pairs of electrons. Now let's see if everybody's happy. What we've got is 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, whoops, oh, 8, and then 2, 4, 6, 8. Everybody's happy. I can't believe I just did that. Sorry. Alright, welcome to the back side of your homework, or we'll have more fun on back. Let's name this molecule right here. It's going to be called silicon, because there's just one of them. and then dioxide because there's 2 oxygens. Now, remember, the next step, first step actually, in writing a Lewis structure is to count up your valence electrons. Silicon has 4, oxygen has 6, and I have 2 oxygens. That gives me a grand total of 16 valence electrons. Because silicon needs the most, having only 4, I'm going to put it in the middle. So I have silicon. I'll put the oxygens symmetrically around it, one on either side. Connect the oxygens to the silicon with single bonds. That's 2 4 electrons. I'm going to distribute the remaining ones in pairs. So 2 4, 6, 8, 10, 12, 14, 16. Just ran out. Now I want to see if I have octets. 2 4 6 8. I have an octet for this oxygen. 2 4 6 8. I have an octet for this oxygen. But 2 4. Wah, wah. Silicon is not happy. Silicon needs 2 more pairs. So I need 2 more pairs to make it happy. So for each pair short, I draw a bond. One here, one here. And then I have to erase a pair for each bond I drew, so I don't end up with more electrons than I'm supposed to have. And now that is what our silicon dioxide molecule is supposed to look like. Let's move on to the next one. It's called dinitrogen because there's 2 nitrogens, and tetrafluoride because there's 4 fluorines. Now I could take nitrogen and fluorine and make a million different well, okay, that's a little bit of an exaggeration. I can make a bunch of combinations out of it, and that's why I have to use the prefixes to tell you, because you could do NF4, you could do NF3. There's a lot of different things you could do here. So I have to tell you in order to make sure you know what molecule it is. So now let's go ahead and figure out the Lewis structure. So each nitrogen brings 5 valence electrons to the table. So I have 5 plus 5 plus 7 plus 7 plus 7 plus 7 for the fluorides. So that's a total of 38. I'm going to put the nitrogens in the middle. I'm going to connect them with single bonds. 2. And then I'm going to put the fluorines around it. Connect them to the center with single bonds. Let's see what I've got here. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. There you go. That's my N2F4 dinitrogen tetrafluoride molecule. Let's go to the next one. Again, we should, since it's a carbon compound, we should be using this one should be called ethene, because that's the rules for naming carbon compounds. But we're not. We're going to use the standard notation that we've been using all along. So here's what we're going to call it. So it's dicarbon tetrahydride. So now let's go ahead and do a Lewis structure. Each carbon brings 4 valence electrons to the molecule, so that's 4 plus 4. Each hydrogen brings 1, so that's another 4 since there's 4 hydrogens. So what I have here is a total of 12 valence electrons to work with. Carbon I'm going to put in the middle. You never put hydrogen. Now this is worth pointing out. I haven't said yet. Yeah, I should have said this. You never put halogens or hydrogen in the middle of the molecule. They are always peripheral because they only want to make one bond. So you don't make double bonds with halogens, and you can't make it with hydrogen either. So with that in mind, I'm going to put the carbon in the middle, connected with single bonds, distribute the hydrogen symmetrically around it. 1, 2, 3, 4 hydrogens. Connect them to the central atoms with single bonds. Now let's count up how many I've used so far. I've used 2, 4, 6, 8, 10. and I have 2 more I can use. There they are. Now look here, I've got happy hydrogens all the way around, but I've got a carbon molecule, a carbon atom that's not happy. It's only got 2, 4, 6. I am 1 pair short, so every time you're a pair short, for each pair short, draw a bond right here and erase a pair. And it'll be this one right here. Now you'll notice I have 12 electrons, 2, 4, 6, 8, 10, 12. But each carbon has 8, 2, 4, 6, 8, 2, 4, 6, 8. And the hydrogens are happy because they each have 2. Yeah, we're done with that one. Let's try the next one. This next one, alright, you know what the name of this next one is called oxygen. Alright, it turns out that these names we've been doing are compound names. And a compound means you have 2 or more elements that are bonded together. But I only have 1 element here. Now this is an example of one of the 7 diatomic elements, which I like to call the pesky 7s. So we're not going to give it a name, but we can still draw a Lewis structure for it. So it still does form a molecule. So I'm going to first count up how many electrons I have. Each oxygen brings 6 to the molecule, so that's a grand total of 12. I'm going to put the oxygens side by side, connect them with a single bond. That's 2, 4, 6, 8, 10, 12. And now I am 1 pair short of what I need. So for each pair short, I'm going to add a bond, and I'm going to erase a pair. That's what our oxygen is going to look like. Again, there is no compound name for this, it's just nitrogen. So let's just go ahead and draw the Lewis structure. I have 5 valence electrons, and I have 2 of them. That's a grand total of 10. Put the nitrogen next to the nitrogen, connect to the single one. That's 2, 4, 6, 8, 10. I'm 2 pairs short, so for each pair I'm short, I'm going to draw a bond, and I'm going to erase a pair. So I'll erase a pair here, and I'll erase a pair here. There you go. Now normally I would draw the lone pairs here and here, but once we start making molecular models, 3D models, we'll see it doesn't matter. Now this next one is technically called hydrogen peroxide because we have a type of polyatomic ion called a peroxide. However, we're just going to go ahead and follow the standard naming rules we've been using. So in that case, we're going to call this one here dihydrogen dioxide. And we're going to draw a Lewis structure. So each hydrogen has 1 valence electron. Each oxygen has 6. So that gives me 12, 13, 14 to work with. Remember now, hydrogens never go in the center. Hydrogens and halogens never go in the center. So therefore that means oxygen has to go in the center. So I'm going to put an oxygen here, a hydrogen here, and a hydrogen here. And I'm going to connect them with single bonds. I just use up 2, 4, 6. Wait, I should have written this down. I have 14 to work with. Okay, so I just use up 2, 4, 6, 8, 10, 12, 14. Oh, that wasn't so hard. Alright, let's try our next one. It's going to be diselenium because there's 2 seleniums, dichloride because there's 2 chlorines. Let's count up valence electrons. Each selenium has 6. That's 6 plus 6 plus 7 plus 7. So let's see. That's a grand total of, I believe that's 26, isn't it? That's 26 electrons to work with. I'm going to put the seleniums in the middle because I can't put the chlorines in the middle. The chlorines are halogens. They always go on the outside. So I'm going to put a selenium here and a selenium here. Connect them with single bonds. I'm going to put the chlorine symmetrically around it. Connect those with single bonds. I've used up 6 electrons here. 2, 4, 6. I'm going to distribute the remaining 20 now. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That was a piece of cake. Let's try our next one here. It's going to be called silicon monoxide. I have one silicon. Remember, don't use mono for the first one. And since there's only one oxygen, it's going to be monoxide. Alright, so I'm going to count up my valence electrons. Let's see, silicon has 4, oxygen has 6. That's a grand total of 10. I'll put the silicon here. I'll put the oxygen here, connect to a single bond. That's 2 of my electrons. 4, 6, 8, 10. I just ran out of electrons, and it looks like I am 2 pairs short. So for each pair I'm short, I'm going to add a bond, and I'm going to erase a pair. And there's my silicon monoxide molecule. Now let's try doing this next one here. We're going to have to call this one sulfur trioxide because there's 3 oxygens. And here we go. Count up valence electrons. Sulfur has 6 and oxygen has 6, and I have 3 oxygens, so that equals 24 valence electrons. I'm going to go ahead and put the sulfur in the middle because I have the fewest of them. That's another way to decide who goes in the middle. And I'll put the oxygen symmetrically around it. I'll connect the peripheral atoms to the central atom with single bonds. Now let's count how many I've used. 2, 4, 6. So now I'm going to go ahead and distribute the remaining in pairs. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And you'll notice I'm a pair short. So if you're a pair short, what do? You add a bond and you erase a pair. And it turns out it doesn't matter which of these 3 places I put that double bond. It's actually forms what's called a resonance structure, and evidence shows that it will bounce back and forth between these, so it doesn't matter where you do it. And there we are done with our homework. I hope you enjoyed it as much as I did.